The other ones, omega final, is equal to omega initial plus alpha t. Omega f squared equals omega I squared plus 2 alpha dot delta theta. And I guess the last one is delta theta is equal to omega initial plus omega final over 2 time. Matter of fact, it works for more than just that. There it is. F equals ma. There's a rotational analog for that too. I know that A becomes alpha. So what are the rotational analogs of force and mass? So we'll just start out with mass. What's the rotational analog of mass?
Mass.
It is not. It deals with how difficult is it for an object that is rotating to stop it or to get it going, because things rotating when it can keep rotating. The symbol is a capital I. It is known as the moment of inertia. There's a fancier name for it that I'm blanking on right now. Also, some textbooks will now start calling it rotational inertia. Not as big a fan of that one, but I understand. It's a measure, just as mass is a measure of inertia, even though mass is not inertia. This is a measure of rotational inertia. And then the rotational equivalent of force is G2 Kumbuka. Otherwise known as torque. I will not explain the G2 Kumbuka reference. I think it's hyphenated there. Torque is what the physics textbooks say. To date, I have had only one student, without looking it up, understand the G2 Kumbuka reference. And that's because he listened to his father. To the best of my knowledge, his dad and I were the only two, and the son, only 3 people who knew the reference.
Sounded like some R2D2 type
No.
thing.
All right. Oh, wait a second. At this point, I know kinetic energy. Well, you know, everybody, come on.
1/2 mc squared.
The chorus of angels with enthusiasm. All right. What would rotational kinetic energy be?
Say that again?
What is the formula for rotational kinetic energy?
1/2 I omega squared.
Now, when I had you memorize 1/2 mv squared, I said you're working on your doctoral dissertation or your Nobel Prize winning work. That's the formula. And now I'm suddenly saying there's another one? This is if you did that to something rotating. This is at the heart of this. All right, so let's concentrate on this for just a moment. Oh, actually, before we do that, we'll take the simpler one. I have an angular velocity. Just happen to have a wheel sitting right here. It's a vector, therefore it has a direction. What is the direction of rotation? What is the direction of the angular velocity?
To the left.
What are you looking at when you say to the left?
The way it's rotating.
All right, so that's moving to the left and that's moving to the right. That's moving up and that's moving down.
Is it measured as clockwise and counterclockwise?
All right, so which way is that spinning?
Clockwise.
It looks counterclockwise to me.
Oh my god.
How do you express direction of something? So clockwise, counterclockwise is used a bit in certain situations, but in general, it's very difficult to do because properly, well, if you're standing in the middle of the room and the wheel is spinning near the front of the room, it's clockwise. That's a lot of wording. So we need a different way of dealing with it.
Say one way is positive, one is negative, something like that.
Rotate.
Yeah, but positive, negative, it depends on what you say it is. All right, so they had to come up with some way of doing it, and they came up with the right hand rule. It is not the dominant hand rule. Any left-handed people in here?
Dexterous.
Whoa,
Whoa.
that's probably the largest left-handed group we've had.
Hey, yo.
It is not a dominant hand rule, it is a right hand rule. I've had left-handed students in the past constantly get this thing backwards, and eventually they get to a certain point where they realize, okay, I'll use my left hand, and then the answer is the opposite of what I come up with. Whatever you need to do, just, it's a right hand rule. So, I have something spinning here, there's an axle. This part that's not moving right there in the middle. The thumb is for this technique. The thumb is pointing along the direction of the axle. So my thumb's pointing this way or it's pointing that way. My fingers curl in the direction of movement. So if it's rotating like that, I put my thumb pointing towards the front of the room because the wheel's spinning around like that. Are you seeing it, Jaquan?
I'm confused.
All right. So as this thing is spinning, it's spinning around like that. So if my thumb is sort of the axle, the wheel is spinning around like that. So we're just establishing thumb would point toward the front because the wheel is spinning that way.
Okay.
If I turned it like this, my thumb would point up. Because again, my thumb in the direction of the axle is either up or down, and the wheel is spinning around like that. The thumb is pointing in the direction of the vector. So when it was spinning like this, the direction of the angular velocity is towards the front of the room. That is now the direction of the angular velocity is towards the back of the room. Angular velocity there is up. Angular velocity there, down. Thumb parallel to the axis and fingers curl in the direction of the rotation. If we open that door, what would be the direction of the angular velocity of the door as it opens? Yep. Now, when I was first taking physics and being told that the angular velocity, say in this case right here, was pointing towards the front of the room, I had a hard time getting to the point where I was trying to think, what is physically moving towards the front of the room? Nothing. Nothing is physically going towards the front of the room. It is a mathematical convenience that actually works. And there's a theory which binds it all together, or there's mathematics behind it all, which I won't go into. But it is just a matter of keeping track of it. So if I said I have a wheel spinning in the room and the angular velocity is towards the front of the room, it doesn't matter where you are, everyone knows then that the thing is rotating around like that. Because that's how you get the velocity towards the front of the room. Questions here? Angle, similar way. I have this thing here and it moves to there. There's a little crack in the wheel here. So as that slit goes from here to here, my displacement, angular displacement, is towards the front of the room. As it went from here to here. It rotated that way. Torque. Questions on direction before we talk about torque?
How would you write the direction on a paper if you're doing the assignment? When you say one way is positive?
All right, so we're now dealing with a third dimension. And probably should not use that on here. There it is. So if I have to the right is I hat, and up is J hat. The way you would do a third dimension there is, imagine you have an arrow being shot right at you. The point, you'd see the point. So if you see a point there, that's out of the page. If it's going away from you, you'd see the feathers. Now, feathers on an arrow do not look like I'm about to draw them, but it's just a memory trait. So this would be out of the board. That's into the board. If I is to the right and J is up, K hat is coming out of the board. This is known as a right-handed coordinate system. Now, right-handed coordinate system, we need some better way of defining it, which will also play into what we're dealing with torque. In a right-handed coordinate system, I hat cross J hat is equal to K hat. We are now getting into the second method of multiplying vectors. We dealt with dot products with energy and work. We're now dealing with cross products. If I have two vectors, A and B, A cross B, this is known as a cross product. Also known as a vector product. For the purists in the group, it actually produces an axial vector or a pseudo vector instead of an actual vector, but the difference between a vector and an axial vector or pseudo vector is nothing that we have to worry about in this class. So it's going to produce some vector. So that means the answer has a magnitude and direction. Unlike dot products, which is a scalar product, this has a magnitude and direction. So before, when I talked about multiplying vectors, I talked about that if we broke A up into its components, some angle theta here, this would be A sine theta and A cosine theta. With the dot product, we multiply the parts that are in the same direction, so that you get AB cosine theta. With cross products, you're multiplying the perpendicular components. So the magnitude of C would be AB sine theta. So if vectors are perpendicular to each other, we're at 90 degrees, what is the sine of 90 degrees? So this is at a maximum when they are perpendicular to each other. If they're parallel, we get 0 degrees, sine of 0 degrees, or 0 radians, is 0. So there is no cross product. The direction of C. I have two vectors, A cross B. The order matters here. With dot product, it doesn't. Commutative property holds for dot products. It does not hold for cross products. I put my hand in the direction of the first vector, A. A is pointing up like that. My hand, I got basically 360 degrees of freedom right now. I'm crossing it with B. B is down, B is that way. So when I put my hand, so my fingers will bend in the quickest direction towards B, and my thumb points in the direction of the vector. It's right hand rule. Again, right hand, not dominant hand. A, B. So the direction of C in this case would be into the board. Let's clear this up some. So if I have I hat cross j hat, and I say I hat is this way, j hat is that way, well, I put my hands in the direction of the first vector so that my fingers bend towards the second vector and my thumb points in the direction of the cross product, outwards. J cross K. I'll put my hands in the direction of the first vector so that my fingers bend towards the second vector, which is pointing outwards. That's I hat. I cross K.
Is it J hat?
It is not.
Is it negative J hat?
Yes, it is. I, K is that way, I is that way, so I cross K points downwards. Negative J hat.
And K is out of the war, right?
Yes. Signified by the dot right there. Apparently I can't think of a larger dot. Now, in terms of, for right-handed coordinate system, if I imagine I got I, J, and K, and I can repeat it, I, J, K. If I'm going in alphabetical order here, I, J, K, the cross product is positive. If I go opposite, it's negative. So I cross J is K, J cross K is I, K cross I is J, then I start repeating myself. The other direction, K cross I cross K. Here's my I and K. If I'm going from I to K, I'm going in the negative direction, so I cross K is negative J. K cross J is negative I. And then K cross, I just did that one. J cross I is negative K. Questions to hear? All right, what are we gonna do? Let's take a small break here, stretch legs. We'll come back and then we'll talk about how to open and close the door. Because I'm sure none of you know how.
To open and close the door.
Right.
Damn, I've been lied to my whole life.
Those who missed it, Kristen just walked in and expressed the incredible joy of coming into a physics class.
I love physics.
Who doesn't? All right, so it's really helpful if the door were on the, came into the room. So, there we go. Our pretend door.
Very, very nice, Dr. Fox.
All right.
I'm glad to see it.
I hope that it was everything you dreamed it would be.
You know of your.
All right, so we have our pretend door here. This will make some good video.
Wait a minute.
This is the door.
I thought you had a daughter.
When I wrote that, I had just a son.
Oh, okay.
When I wrote the other one, I had a daughter
Oh, okay.
also. Actually, my daughter came to my defense, my doctoral defense. She did not cry.
Good for her.
All right, so how do I close this?
Knock it over. Squeeze it together.
Squeeze it together. Be more specific.
Shut the door.
Can we What part is the door, part of the door frame?
This would be the door frame, this is the door.
So.
We're on
Bring it towards you.
Push that, okay, that didn't work.
Pull that from your direction.
Pull it from my direction. That didn't quite work either.
Do I need to go up there and show you how it's done?
I need you to explain to me how it's done.
Shut it with some force.
Shut it with a force. How do you shut the door? You just shut it.
Put your hand behind it. Other side.
Why is that behind?
It's
Because
behind
you're
you.
in front.
Put your
I'm
hand in
behind.
front of it.
Grab a hold of this, grab a hold of it right
Swear to
there,
God.
now bring your hand to the door frame. While holding it.
You need to flex your biceps brachialis muscle in a direction
Oh,
towards
don't
you.
get all fancy with the doors.
Grab the door with your right hand
Alright,
upon the border and bring it to the door frame with your right hand.
I can't do it with my left hand.
No.
Has to be.
Right
Yeah.
force.
So, I grab a hold with my right hand
Yep.
and then bring my hand.
Bring your right hand to the door frame while still holding the door. That's close to Jeff me.
Is it?
Technically,
Not
it
according to my
is.
parents, so.
Maybe this is a multiple step process. Maybe that was step one. Now, step two was to take your hand out and finish closing it.
And how do you finish closing it?
Put your
By
hand on the
slamming.
white
Let the
You
side,
gotta slam it.
Put your hand on the white side.
this white side, and then,
I will assume of the door,
Yeah.
because there's a white side over here. Alright, so put my hand on the white side.
and pretend like you're trying to hit yourself in the chest like this. And that should be enough force to close
Alright.
it.
I swear to God.
So if I'm closing this, you're just saying I just need to push from this side, right?
Sure.
With constant force.
It's not particularly easy. Is there a simpler way of doing it?
Just high five the door until you can't high five it anymore. Pushing it.
It still doesn't seem particularly easy doing it that way. Is there a more efficient way of
Maybe
doing
if you
it?
had a handle, it'd be a lot easier. So it could latch.
I think it'd be easier if you did that same thing on this side.
On this side?
Yeah.